So on the chart here on the energy pathway, the laminate, we can see we've divided it up into the three parts, the 1, 2, 3, which I talked about earlier. Glycolysis, which is anaerobic, and then the citric acid cycle inside the mitochondria here, and the electron transport, otherwise known as oxidative phosphorylation, which is aerobic, and therefore aerobic means it requires oxygen. So if we look a little closer at the glycolysis pathway here, behind home in iron, we'll see that every single pathway here involves magnesium, which is why I said magnesium is the key element to glycolysis. But you won't find too many people show to this as the pathway problem. We do get sometimes people will strengthen to pyruvate, in which case there's no need to chisel back through each of these because everyone is dependent upon the same cofactor, which is magnesium. So if we have a look at the space between the mitochondrial membranes, the outer membrane here and the inner membrane here, this little area is very interesting because this converts or oxidizes the pyruvic into the acetyl-CoA. So let's home in on there a little bit, because if we get a blockage here and then we get a build-up of pyruvate, we then have a situation when people weaken to pyruvic acid because they've got too much of it, because it's not able to be oxidized through to acetyl-CoA. So this person would strengthen to acetyl-CoA because they've got a deficiency of it, and weaken to pyruvic acid. So we would then know there's a problem here, an inhibition, which is an expression of the enzyme or lack of expression of the enzyme. And we would then look at the nutrients to stimulate it. And the major one here is pyruvate dehydrogenase enzyme, which requires vitamin B1. There's only 2 or 3 enzymes in the body that use thiamine or vitamin B1, and this is the major one. And the active form of this is called thiamine pyrophosphate. So thiamine pyrophosphate, or the active form of B1, is involved with the dehydrogenation, in other words, the removal of a hydrogen here to convert pyruvate into CoA, into acetyl-CoA. Now the CoA part is an active form of vitamin B5 or pantothenic acid. So this comes in as the reduced form, CoAsh, is the reduced form of coenzyme A. So this is vitamin B5. So now we need B1 and B5 come in here. And then we rotate here using the coenzyme alpha lipoic acid here, the transacetylase enzyme here, which reduces alpha lipoic acid and then oxidizes it again. And this recycling of this depends upon vitamin B2 and B3. So now just this little pathway between the outer membrane and the inner needs B1, B2, B3, B5, and alpha lipoic acid. But the main coenzyme here is vitamin B1. So if you're deficient in B1, you simply can't get in to the Krebs cycle. So one of the first symptoms is tiredness. Now you see tiredness in the areas of the body that use more energy, that require more energy than anywhere else. And the first one is the neuron, or the brain, and the second one is the muscles. So you get tiredness in the muscles, but you get tiredness in the brain here, and the areas of the brain that use more energy than anywhere else will be the ones affected, and they get what's called a neuritis, or maybe a neuropathy, because they're not making enough of the energy there for the pathway to work properly. Now, one of the places you get that is in the peripheral neuropathy, you know, when people get loss of sensation in their feet and the hands, and sometimes in the eyes. It's called optic neuropathy when they start to lose the vision. So there may be the loss of certain parts of the vision in the center or the periphery, and this is called optic myopathy and is a vitamin B1 deficiency. So when people have got eyes, don't think, oh, just lutein zeaxanthin, which we'll talk about when we look at hypoxia, but B1 is a very, very important part of this as well, as thiamine pyrophosphate is the active form there. Now, if we don't make enough acetyl-CoA, we then haven't got the acetyl part. So acetyl-CoA goes on as the substrate to make citrate, etc., around in the Krebs cycle. But acetyl-CoA goes on to make other things where it leaves the acetyl group. So acetyl group goes on to make a very important neurotransmitter called acetylcholine. So this means that if you can't convert pyruvate to acetyl-CoA, you can't make acetylcholine in sufficient amounts, which means the whole of your parasympathetic nervous system doesn't work properly, including the vagus nerve and all the parasympathetics, or your neuromuscular junctions. So these are all very, very important pathways, because if you don't make acetylcholine, your neuromuscular junctions, you start feeling tired in the legs and aching in the legs. So, and the last part of this, of the acetylation, very important, is detoxification. It's a phase 2 detoxifier. So people with poor acetylation have poor detoxification of certain chemicals. And one of those is benzene or petroleum. They're very sensitive to petroleum. And I find, I have a problem here myself, is I find there's a chemical in newsprint that if I open a newspaper up and it's fresh, sort of newspaper, there's a smell to it. And the worst thing is colour supplements, because the ink is very, very cheap on that. And over there, and I'm starting to read this, and then after a moment it gets a bit blurry, and I'm not too worried about that. And then I start to sting. And there's chemicals coming off as a vapour and getting into my eyes, and it really starts to sting there. So I realised that it's the newspaper or the magazine that I'm reading, and I have to put it away there. But of course the focus depends upon acetylcholine to pinpoint the pupil of the eye, the constriction of the pupil, to be able to home in, to be able to read, is under the auspices of acetylcholine through the ocular aortic nerve. So if you're not producing enough acetylcholine, you start to lose the focus. So you may be other areas of the body parasympathetic affected, but the major one is going to be the eyes. So when people have vision problems, this is going to be acetylcholine. So people who are long-sighted, so we can see distance, but you can't see short so close up. This is a lack of acetylcholine, because you can't pinpoint, you can't make the pupil smaller. Okay? People who are short-sighted, as you can see here, but can't see distance, can't open their pupil up, and the opening of the pupil up is noradrenaline, so that's sympathetic nervous system. So they're opposites, if you like, opening and closing the eye. One is sympathetic, one is parasympathetic. So that's the balance of the two. So acetyl-CoA is not only there as a substance to spin the Krebs cycle to make energy, but it's involved with detoxification, and it goes on that acetyl group also to make acetylcholine. So alpha-lipoic acid is a substance which is a universal antioxidant, and it's universal because it's fat-soluble and water-soluble. It has a number of different factors. It's a sulfur-bearing compound, and it gets the sulfur from the amino acid cysteine. And that sulfur has a valency of 2, of 4, and of 6. So it has 6 arms potentially that it can connect onto. And the sulfur can therefore reach out and get hold of metals, particularly toxic metals, and help to bond onto them to detoxify. So alpha-lipoic acid is, if you like, the universal chelator of toxic metals in the body. So if it becomes occupied with these 2 sulfurs occupied with toxic metals, it then can't function in that pathway between pyruvate. So again, people get heavy and tired who've got high levels of toxic metals in their system. So to make alpha-lipoic, we need the amino acid cysteine and octanoic acid, otherwise known as caprylic acid, which is a carbonate saturate. And to convert that, we need thiamine, pyrophosphate. So this is the second function that we come across to actually make thiamine, that uses thiamine. So now we know thiamine is involved in the conversion of pyruvate to acetyl-CoA, but it's actually necessary to make alpha-lipoic acid, which does the recycling itself. So we find also alpha-lipoic works really well when people have blood sugar problems. So usually with when they got blood sugar handling problems and they get hypoglycemia, alpha-lipoic acid may help in these type 2 diabetic cases. So alpha-lipoic is an antioxidant, it's a chelator, and it stabilizes blood sugar levels. Now, the Krebs cycle. So it's basically what's called an oxidative process, which means the loss of electrons. So acetyl-CoA goes to citric, or otherwise known as citric acid. So this is why we tend to put a lot of our products as citrates in capsules, and also to put citric acid in to minerals. It seems to activate the mineral to get it to work better. I first came across this a few years ago with silver, that we started adding a little bit of citric acid to the silver, and it worked much more effectively as an antimicrobic. So citric acid has antimicrobic properties. So citric acid is a component, it's a natural substance to the body because it's in the energy pathway here. Citric goes on to isocitrate, to alpha-ketoglutarate, to succinyl-CoA, to succinate, to fumarate, malate, and oxaloacetic acid or oxaloacetate. Now, you'll see here that this pathway has an arrow here, so it only goes this way. This one goes both ways, this one goes both ways, but this one only goes this way. This one goes both ways, this one goes both ways, this one goes both ways, this one goes both ways. That means the cycle can only go clockwise, because when we get to here, it can't go back, right? So it has to go forward all the time, and here it goes forward. And these are the stopping bits, so we don't get any sort of re-going back in the Krebs cycle, and it can only go in a forward direction. And the speed that this turns, the cycle, the speed that we convert acetyl-CoA round to oxaloacetic acid and give off then the FADH and the NADH, this depends upon thyroid hormones, the thyroxine. So the T4 converts to T3, as we described earlier, by the deiodinase, which is that selenium-dependent enzyme. So the first thing you get when you have a sluggish thyroid is you get a slow metabolic rate. So the metabolic rate is the speed that we turn the Krebs cycle. And remember that 80% of the energy we produce goes to heat. So the first thing people get is they feel tired, but they get cold. And the way we measure that is the axillary temperature first thing in the morning. So before you got out of bed and started walking around, which will increase your metabolic rate, you just put a digital thermometer into the armpit and just wait for it to ping. And when it pings, it's been the same temperature for a few times. And then you look at it, and if it's below 37, you've got a sluggish thyroid. Okay? So it may not be the thyroid itself, but it's usually, in most cases, it's the conversion of T4 to T3. And that enzyme, the deiodinase enzyme that does that, is selenium dependent. And selenium, as we know, is a trace element which is getting more and more deficient in our food. Okay, we found that a very good source of this was watercress. Watercress is one of those substances, one of those compounds which can make, or if they thought, transmutate anything from anything. So it's a wonderful substance. It may be able to actually generate selenium from the minerals within the stream, within the water. But nonetheless, it seems to absorb, and it is a very good source of selenium. The books will tell us Brazil nuts, but half the Brazil nuts are good in selenium and the other half aren't. It depends on the soil that the Brazil nuts are grown in. And it does appear that the half which don't have the selenium are actively got radioactive material in it. So where the Brazil nuts seem to grow, be very, very careful, muscle test the Brazil nuts, because most I find don't actually treat people, or don't test positive for people with selenium deficiency. But there is one substance, one food, which is still very, very rich in the right type of selenium, and that's camel wheat. Camel wheat is something, it's an old-fashioned wheat, which was discovered originally, the story, in the pyramids. But there was an American farmer who was on service duty in Egypt in the 1950s, and when they went into one of the tombs, one of the pyramids, they found these jars or bowls of containing wheats from the pharaoh of 4,000 years ago. And he, being a farmer, he wondered whether the wheat would still grow. So he took some of it and he farmed in Montana, which is a big agricultural state in America, and he found it did grow. And not only did it grow, but he had it analyzed, and it was a very simple, it had half the number of chromosomes that modern wheat or even spelt has. So it was very easily digested with people with wheat sensitivities. This was in the 1950s and 1960s. By the 1970s, it was all considered to be rather cranky. It's going back, we're going forward into modern wheat, you know, with bigger heads and more gluten for making bread, etc. And it almost went extinct again. But his son, who became the farmer after the father retired, went back to it because it was then becoming a bit of a cult to grow older products, older vegetables and fruits. And it took off. And when he had it analyzed that modern labs can do, he found that the fatty acid content was remarkable. It had omega-3 oils. If you go to the website now of Kamut, that's Kamut, You can read all about it with the exact location. We put some of the information onto our website now because it tells you the story of it, and it tells you the fatty acid content, the proteins, the amino acids that it's got, the minerals, and the major thing is that it's selenium. It's the highest content of selenium, and not only is it selenium, it's selenium phosphate, and that's the critical thing. It's the only food really that muscle tests when a person strengthens to selenium phosphate. You'll find that camel wheat will do the job, so it's got the phosphates in it. The story is now that Montana and South Dakota are the main areas where the selenium level is still very high. In this country, the selenium levels, the only area where selenium is really high is East Anglia, which is reclaimed land, basically. And it just happens that people live the longest in the world where the selenium levels are high. So you don't have to put two and two together to know that selenium is rather important, not just for the thyroid, but 25 different enzymes in the body use selenium. And probably more important than the thyroid one is the glutathione peroxidase enzyme, which detoxifies us and uses glutathione to detoxify. And the glutathione peroxidase enzyme is the antioxidant that recycles glutathione. So glutathione is an amino acid complex, which is a detoxifier, and it's the most powerful intracellular antioxidant. So what I suggest is that you look at about camel wheat, and you think about using camel wheat in your diet. Very easy to mill it and make bread, but it tastes nice as well, and this is the thing. But it's the richest source of selenium, natural source of selenium, that there is around. Story has it that Alexander the Great conquered half the world on Egyptian wheat. This was before the time of Christ, so he would have used camel wheat. Now, the biggest exporters or biggest importers of camel wheat, because this farm in Montana and South Dakota is the only place in the world he has the patent on it now of camel wheat, but they grow it, and the biggest importers are the Italians. So the Italians, when you go to Italy now, you see camel wheat for sale as pasta, camel pasta, camel pizzas, and camel bread. So that's where we first saw it a couple of years ago in Sicily, and we thought, what is this stuff, you know? And then we started investigating it. But now you can buy the camel wheat, and it makes delicious as a freshly ground grain, and it's a rich source of selenium. So I think the reason for the thyroid problems is a gradual deficiency of selenium available because of the intensive farming. So it's no longer in wheat, which of course it would have been, because they grow wheat and wheat and wheat on the same field, and they replace, you know, with phosphates and nitrates, but they don't put selenium back in the soil. One of those things are, it's only micrograms, you don't need to bother about that. It'll come in the rain, but of course it doesn't. So selenium is probably becoming deficient in large parts of the country because of intensive farming. And so we're getting this build-up of toxins, chemical sensitivities because of glutathione peroxidase, and thyroid problems. So the spinning of the Krebs cycle depends upon the thyroid hormone, and the sole purpose of the spinning of the Krebs cycle is to put a hydrogen, or two hydrogens in this case, on FAD, the coenzyme of vitamin B2. So we see here we put FADH2, and a hydrogen onto NAD to make it NADH plus an extra proton here. So now we've got two end results. So FADH2 and NADH are really what we're spinning the Krebs cycle about. And those are the main purposes of to donate the hydrogens to pop into the membrane between the inner membrane here and the outer membrane. And as I said before, the hydrogen is the simplest atom, which has one electron and one proton. So directly it splits, which means we've got an electron and we've got a proton. So every time we put two hydrogens in, we're going to get two protons and two electrons. So our NAD is a vital component of what's called complex 1. FADH2 is a vital component of complex 2. So we've got two electrons going at 1, 2 at 2, 2 and 2 make 4. So 2 here and 2 here make 4. So 4 electrons are carried by coenzyme Q10. So coenzyme Q10 is a carrier of the electron. It's an antioxidant, but it's also a carrier of the electron now to complex 3. Now, complex 3 is made of cytochrome compounds, which are based on heme, which we'll see when we talk about hemoglobin, the same way of making it. So this is a heme or cytochrome compound, which then converts it carries the 4 electrons to complex 4 by cytochrome C, which again is a cytochrome or heme-dependent enzyme, to complex 4, which is called cytochrome C oxidase. So now we've got complex 1, 2, 3. So we can measure by using complex 1, 2, 3, and 4 where our problem is exactly in the electron transport chain. So we'll do that in a minute. Previous to this, we had to use poisons, which are known like rotenone, like rat poison and things, which are known to inhibit complex 1 here, as markers for possibility of where there's problems in the electron transport. But now we've acquired these complexes, we can actually measure precisely with a person where their blockage is. So if you remember here at complex 4 is where oxygen enters, and the only place where oxygen enters, 90% of the oxygen that we breathe in goes into this part of the mitochondria, and its simple job is to carry the electrons, the 4 electrons, from complex 4, to take the 4 electrons and be converted into water. So it says, thank you very much, I'll take the electrons. But if it takes 1 electron, 2 electrons, 3 electrons at a time, we may end up then with a cascade of reactive oxygen species, as they're called, often miscalled free radicals. So if we add 1 electron to oxygen, to molecular oxygen here, we get a molecular oxygen with an extra dot on it, or an electron. This is called superoxide. So you'll come to learn to love these because they're inflammatory chemicals. And they're here for a reason. Because if this was a white cell, it would be necessary to make these reactive oxygen species to kill bacteria. That's what the job is. They're oxidizing, just like putting household bleach on. So if we want to kill something, we will need to oxidize it or bleach it. So this is why we have this system. But we don't want this system going on when we haven't got an infection. So if our white cells and other cells are producing reactive oxygen species, which will cause inflammation, we'll get damage ultimately, and we've got to then take more nutrients to try and repair. When we add 2 electrons, the second electron, we get H2O2, which is hydrogen peroxide. So if you pour that onto your skin or your hair, you'll soon bleach, and you'll see what it does. Okay? Now, we produce hydrogen peroxide mainly to kill parasites. So the white cells that produce this, the cells that eosinophils, which kill parasites, are specialists in producing hydrogen peroxide. So hydrogen peroxide is a very strong bleaching agent. If we add 3 electrons, we then get hydroxyl radical, and a hydroxyl radical is very damaging, particularly to the DNA. Not only does it damage one side, like a nick it's called, on the side of the DNA, of the ladder, but it can damage both sides. And if you damage both sides of the ladder, you haven't got the template to copy to repair the DNA. So that way the DNA ladder collapses. If you've got damage on one side, which could be caused by superoxide or other reactive oxygen species, you can copy that from the other side. So the body's able to repair. And remember, the enzyme that does that is DNA polymerase, and DNA polymerase is a zinc-dependent enzyme. So the major symptom of zinc deficiency is poor repair. So tissues don't repair if you're zinc deficient because of DNA polymerase. So we need DNA polymerase. When we add 3 electrons, we get the hydroxyl radical, which can damage both sides. So this is really why we call it the dreaded hydroxyl radical. And when we add the 4th electron, we get H2O and oxygen. So it's a clean machine, provided it works well. But it's a dirty machine if it only has 1 electron added, or 2, or 3. Okay? So why would you not have all 4 go on at once? Because this is happening so quickly, so rapidly, at thousands of times a second, and the electron has to go from complex 1 to 2 to 3 to 4. If there's a problem in 1, 2, 3, or 4, and the electron is not carried correctly, then there could be an issue where we don't get the electrons in the right sequence. And that could be because we're deficient in any of the components that make up complex 1, 2, 3, 4, or in coenzyme Q10, availability there of making CoQ10, or within the carrying molecules of the electrons in the complexes. And these are called heme. So heme is a substance which we'll see when we talk about hypoxia, which is light sensitive and can carry the electrons from one complex to another. And if it's not formed properly, well, then we won't get the electrons on 4 electrons on in one go. This is an old picture. I've used this with teaching for many years because it's one of the best I've seen. So here we've got the Krebs cycle producing the FADH2 and the NAD coming in here. So we've got NADH and FADH2. NADH goes into complex 1, and each molecule will produce an electron there. Complex 1. That electron, or 2 in this case, go on to CoQ10. 2 more electrons go in there on complex 2 from FADH2. This has now put 4 protons into the membrane here. See all these H pluses as they build up here. They're carried from CoQ10 to complex 3. Then by cytochrome C, which is a heme-dependent carrier, to complex 4, where molecular oxygen converts to water. So this is where it all happens in this area, or complex 4, is where the conversion of oxygen takes the 4 electrons and produces H2O. In between time, the concentration of the protons has continued to complex 5, and this then goes through, the protons burst through complex 5 and activates an enzyme called ATPase, which simply puts the phosphate onto ADP to make ATP. Now, I didn't invent the system, but I admire the scientists who studied it and worked out how it works, because it's amazing that anybody can actually do that on some structure which is so small. And the reason that they were able to work a lot of this out was they could work out poisons which inhibited the various pathways. So they knew that certain poisons, like cyanide, would inhibit complex 4. Works very efficiently. Within seconds of putting cyanide in the mouth, the complex 4 throughout the whole body goes. Rat poison, it's mainly the way that rat poisons and pesticides work, is usually to decrease the production of energy in the mitochondria. So gradually, from working from the poisons of how they work, they were able to actually work out what the system was all about as far as converting it. What we now know is a lot more detail about the components, the nutritional components that we might consider in the energy production. We know the result of poor energy production through lack of oxygen is an increased amount of free radicals. So if you decrease the amount of oxygen here, if you imagine decreasing it there, we're going to get a build-up of electrons. So we're going to get more abnormal oxygen molecules, more superoxide generated. So every time we generate superoxide, it's then going to become reduced to hydrogen peroxide and the others.